You are welcome to this lecture. We are trying to solve a numerical problem related to plate fin type heat exchanger rating problem or the performance evaluation of the heat exchanger. So, until the last class we have tried to estimate the heat transfer surface area, and also we have evaluated the flow rate mass flow rate corresponding to the air side and the gas side. So, now if we look at we will find that we have estimated the mass flow rate of air, and that is equals to 2.0 kg per second, and then we had the corresponding value for the gas side was 1.66 kg per second. So, this mass flow rate of air and the mass flow rate of the gas, when we multiply it with the corresponding the Cp values, we will be able to find out the C mean or C max, or determine the C mean or C max. Here at this moment we do not know exactly what is the exit temperature of the air or what is the exit temperature of this gas. So, that is what we are supposed to find out, and as we have seen in the earlier cases also, we have to make an rough estimation of this gas exit or the air exit, so that we can take the fluid properties or evaluate the fluid properties at the mean temperature. So, should we go for any wild guess, or should we go for some kind of reasonable estimate of the make a reasonable estimate of the gas exit temperature, that will determine the how close we are to the actual result. So, later on we may have to look for an iterative solution if we are making a very wrong guess about the exit temperatures. So, now we can understand that this mass flow rate of air is slightly higher and than the mass flow rate of the gas. So, if we assume that they are not having much dependence of this Cp of the gas or the air or the Cpg or Cp air, they are not very different or they are not really dependent on the temperature. In that case we can say that this mg or the gas side is the minimum capacity fluid, or C mean will correspond to the gas, and accordingly we have to we can try to find out the fluid properties based on the assumption that let we assume that this heat exchanger effectiveness is 0.75. So, for this cross flow type heat exchanger, this is the assumption we are starting with. So, this assumption will lead to an estimate of the exit temperature on the gas side as well as for the air side, and once we know the exit temperature of the gas and the air, we would be able to find out the mean temperature at which we have to evaluate the fluid properties, and then once we know the fluid properties, we will try to calculate the Reynolds number and the other fluid other properties. So, now if we assume epsilon to be 0.75, we would be able to correlate them with the heat temperature, exit temperature. So, epsilon is equals to 0.75, and since we have assumed similar specific heat for the air and the gas, we know that the gas is the minimum capacity fluid. So, we can say that T air of the T gas of the inlet minus T gas at the exit. This is the minimum capacity fluid, and this is T g of entry minus T air at the entry. This should be the epsilon or the heat exchanger effectiveness. So, from here what we know is the entry temperature of the gas, this gas entry and this air entry temperature is known. So, from this relation we can calculate the gas exit temperature, and this will come out to be 375 degree centigrade. Now, similarly, if we look into the temperature corresponding to the air exit, so you will find that epsilon, that is equals to 0.75, and that is equals to the T air out minus T air in into mass flow rate of the air divided by the T g I minus T a I, that is the maximum difference in temperature multiplied by the minimum capacity fluid, and we have assumed the C p of the air and C p of m g are the same. And so, this is here in this relation you will find that we know the air entry, G entry, gas entry, air entry, and M A by m g ratio is already known to us. So, we would be able to find out T air exit temperature, and this will come out to be 635.8 degree centigrade. So, we have now an idea about the air and gas exit temperatures. So, we can now calculate the mean temperatures, and the gas side mean temperature will now come out to be G m, that is equals to 900 plus 375 divided by 2. It is the arithmetic mean 0.5 degree centigrade, and for the air side we have the mean temperature as 200, it was its entry temperature, and 635.8 is the estimated exit temperature based on the epsilon equals to 0.75. So, that gives you 417.9 degree centigrade as the average temperature. So, now based on this temperature, mean temperature, we would be able to calculate the fluid properties of the different fluid properties, like what are the fluid properties we need, the mu we need, the Cp we need, then we need the Prandtl number, and Prandtl number obviously these are the parameters what we will now require for. And for gas we have the mu equals to 40.1 into 10 to the power minus 6 Pascal second is the unit, and then we have, this is the mu, then we have Cp, that is equals to 1.122 kilojoule per kg Kelvin. Then we have Pr is equals to 0.731, this is for the gas. And for the similar parameters for the air, we have mu is equals to 33.6 into 10 to the power minus 6 Pascal second. Then we have Cp of air, this is Cp of gas. So, Cp of air is equals to 1.073 kilojoule per kg Kelvin, and then we have P air for this one is 0.694. So, these are the values known for the gas and the air. So, based on this value we would be able to now calculate the gas velocity. What is gas velocity for the Gg or mass velocity for the gas side? So, this is equals to mg dot by A free flow area for the gas side. So, both the parameters are known. So, we can now able to find it to be, this is 0.3 meters kg, sorry, this is kg per meter square per second. I am sorry, this is unit is kg per meter square second. And similarly, we can also calculate the mass velocity for the air, and the mass velocity for air will come out as m dot divided by A 0. So, both the parameters are known already. We have able to calculate the mass flow rate, that is equals to 2 kg per second, and this is just nothing but 0.1089 meter square. So, that gives you 18.365 kg per meter square second. So, these are the mass velocities of air and the gas side already known to us. So, when we know about this gas side mass velocity and the air side gas velocity, we would be able to calculate the hydraulic diameter corresponding to the gas side R is G. This will come out to be G d H by mu, and this is the mu of the gas. So, this will come out to be, if we put all these parameters, this is equals to 15.342 multiplied by 0.00154 divided by mu of the gas has been taken as 40.1 into 10 to the power minus 6. So, this will come out to be 589. Similarly, if we try to estimate the R E for the air side, we will find that this is G A mu by, I am sorry, d H by mu of the air side, and if we put all the values, it will come out to be 842. So, now we have the knowledge about the Reynolds number, air side and the gas side. So, corresponding to these values, we will try to find out, we will go to the this diagram where we will be able to locate the, this is nothing but the Stanton number or multiplied by Prandtl number to the power 2/3. Basically, this is the J and this is the friction factor. At this moment, we will not look for the friction factor, we will look into the J factor to calculate the heat transfer, and this is the Reynolds number. So, we have the Reynolds number here, and please note that this is multiplied by 10 to the power minus 3. So, corresponding to that 589 and 842, we have to find out the J factors. So, the gas will have a J factor given as corresponding to 0.0170 corresponding to RE value of 589. This for this RE value, if you look at, we will have this value, and for the gas and the air side we have 0.0134 corresponding to an RE value of 842. So, now we have the J value for the gas and the air. Now, if we have the J value, J we have seen as Stanton number into P air to the power 2/3. This Stanton number contains is H by G C P and P air to the power 2/3. So, since we know this J, we have already estimated G, C P, P air, all these values are known. So, for J corresponding to 0.017 and we can try to find out the heat transfer coefficient of this is for the gas side, and you will find that H G will come out to be 360.83 watt per meter square Kelvin. Similarly, we need to put the value of the heat transfer coefficient corresponding to air side, where we have the J value given as 0.0134, and if we put all those values, it will come out to be 36.81 watt per meter square Kelvin. So, now we have the heat transfer coefficient for the air side and the gas side, and though we are using the similar kind of heat exchanger surfaces, we have different heat transfer coefficient as the mass flow rates or the volumetric flow rates were different, and that corresponds to different RE value, and that corresponds to different heat transfer coefficient for the gas side or the air side. So, now we have the knowledge about the heat transfer coefficient. Next is we need to find out what is the overall fin efficiency. Since the fins are connected between the plates, we need to also know what is the fin efficiency, so that we can put that 1 by UA. Basically, if you remember that in the last in the previous classes, we have told that this is the heat transfer coefficient multiplied by the heat transfer area multiplied by the overall heat transfer coefficient, plus this will be 1 by H G and then A G and eta O for the G, and also we have the wall heat transfer coefficient, the resistance estimated for the wall. So, for this one we will try go later, and already we have evaluated H A, we have already evaluated A G and H, all these parameters are known, and we now need to find out this overall heat transfer coefficient for the gas and air side. So, for that what we need to do is that we need to calculate the m g, that is if we remember that this is not the flow rate, this is related to the fin, where that m the fin efficiency will be termed as tan hyperbolic m into L divided by m L, and here this m we now try to calculate, because we know that m is equals to root over H p by K A. H is the heat transfer coefficient, P is the perimeter, K is the thermal conductivity of the fin material, and A is the cross sectional heat transfer cross sectional area. So, if we put these values for this particular situation, we will find that this is going to be 2 H by K of the fin material, and then we have the delta, that is the thickness of the fin, and then we have 1 plus delta by L S, that is the lance length of the fin, and then we have whole root over. So, this is what is the this m parameter for this eta or the fin efficiency, and we have both for the gas side and the air side M we can calculate from this correlation. So, that will give this m g to be 634.94 and m a will come out to be 615.37 meter inverse. So, here this both L A and L S that has been taken as B by 2 minus delta, that is equals to 249 by 2 minus 0.102, and that comes out to be 1.143 millimeter. Now, the question is, why did we take this B by 2 minus delta? If you remember that in some of the previous classes we have talked about the half fin idealization, there that half of the fin is as if attached to this plate and half of the fin is as if attached to this the upper plate, and thereby this half factor is coming as if this adiabatic plane is there at the middle, and that gives half of the fin. And in fact, for a symmetric configuration like where a two stream exchanger is concerned, we will find that half of the fin is really attached to this upper fin and the half of the fin is related to this lower other fin, plate side. So, we will get into this in details when we talk about the multi-stream plate fin heat exchanger. At this moment, we will assume that this half fin idealization works good for the two stream heat exchanger cases, and we have this L A equals to L G is equals to B by 2 minus delta. So, accordingly we have the M A value, and we can now calculate the eta f or the G, and this will come out to be 0.8581, and eta A for the air side will be 0.8657. So, from there we can now calculate eta overall for the gas side. It will come out to be 1 minus eta A, and then this is eta G 0, and there comes that A by F minus by A. So, this is nothing but this parameter is also given in our calculation, fin specification. So, this comes out to be 0.8886, and for the eta 0 of the A, that comes out to be 0.8946. So, you can evaluate it using this correlation. For this, it will be basically 1 minus eta G eta A overall multiplied by A f by A, and that will come out as eta 0 for the air side. So, now we have the idea about this overall heat transfer efficiency. Now, we can go to calculate the R W. So, this R W is basically the delta W divided by K of the wall divided by A of the wall, and this delta W is the thickness of the fin. So, that is equals to 0.5 into 10 to the power minus 3 meter, and K W is already given 18 watt per meter Kelvin, and this A W is nothing but A W is equals to how many number of layers were there? L 1 into L 2 multiplied by 2 N P plus 2 number of layers we had. So, this comes out to be 30.24 meter square. So, this is quite substantial, and this is 30.24, and this comes out to be this many meter square. So, R W will come out as 9.186 into 10 to the power minus 7 Kelvin per watt. So, this is 9.186 into 10 to the power 7 watt per Kelvin per watt. So, we have now the overall estimation of this 1 by U A is equals to 1 by eta 0 H A for the hot side plus R W plus 1 by eta 0 H A for the cold side, and if we put all the values, we will find that from here U A is coming to be 1 to 985 watt per meter square, sorry, watt per Kelvin, the meter is already here. So, 1 to 985, if it is this many U A it is there. So, now we have to calculate the ratio between the C g is equals to m dot C p of the gas and C A is equals to m dot A C p of the A for the air, and we have this to be 1863 watt per Kelvin. This comes out to be 2146 watt per Kelvin, and then the NTU comes to be U A by C mean. So, this is just nothing but 6.97, and the ratio between this to C r by C mean by C max, that is equals to 0.868. So, we have now these values for the NTU and C r, and then based on this relation we would be able to calculate what is called the epsilon, and we know this relation for the cross flow heat exchanger, and from this correlation if we estimate this epsilon will come out to be 8328. And since we know this epsilon value, we can now calculate the exit temperatures, and also we can calculate the overall heat transfer. So, Q would be epsilon times the T g I minus T air I into C mean. This is from the basic definition of the heat exchanger effectiveness, and if we put all these values, so this is supposed to come nearly to 0.8328 multiplied by, this is the epsilon value, T, this is equals to 900 minus 200, and C mean was whatever value for the C mean we had, 1863 watt per 63 watt per Kelvin. So, if we now evaluate all these things, this will give you some wattage for the Q, and here you will find, based on that Q value, you would be able to find out the T gas side exit temperature and the air side temperature, and you will find that they are not matching with the assumptions that we have made. As you can understand that we have estimated and or assumed an effectiveness of 0.75. So, already we have deviated from there. So, now based on this new value of the heat exchanger effectiveness, we will have two sets of the exit temperature, and based on that value we can now again make another estimation of the heat exchanger effectiveness, and then we can make an estimate of the total heat transfer and then we have to find out that when we reasonably close value are predicted, then we can stop our iteration. So, that is how we have to go ahead with the design or the simulation of the heat exchanger problem. Thank you for your attention.